Hey guys, this is Josh Hall. I'm a senior engineering student here at Arkansas Tech, and today I'm going to be giving you a presentation on modeling DC motors. In this presentation, I will cover the workings of a simple DC motor, including a list of parts and their functions, and some typical uses for a DC motor. Then I will cover the math behind the model before finishing up with how I modeled the system in MATLAB. So let's get started. To start with, I have included a simple picture of a DC motor. Here you can see a list of the main parts of a DC motor. You have the brushes, stator, rotor coils, the commutator, and the shaft. Each part has a specific function, which you can see I have listed here for you. The whole process begins with a DC current coming into the brushes. Some motors are brushless, but for this case I will focus on the motor with brushes specifically. These brushes pass the current onto the commutator. The commutator is a split ring device that changes the input of the current to a different end of the coil each time the coil becomes perpendicular to the magnetic field. This keeps the motor from getting stuck perpendicular and keeps the torque flowing the same direction. The magnetic field is provided by the stator, which is a stationary magnet. This magnet creates a magnetic field which interacts with the current in the coil and creates the torque. And that torque turns the shaft, which can then be used to perform a job, thus turning electrical energy into usable mechanical energy. Here I have listed some typical uses for DC motors. As you can see, a DC motor has two major advantages. This is variable speeds and high starting torque, which makes them useful for things such as robotics, portable toys, household appliances, power tools, and some automotive uses. There's not a great demand, however, in industries, even though some industries call for varying speeds. In these places now, however, you'll see inductive AC motors. In these next two slides, I cover the math behind the model which I chose. I have added here the transfer function of the DC motor, which I modeled in MATLAB. This next slide includes the block diagram of my system and the structure which I followed. After these mathematical models, I have uploaded my design requirements. I decided to go with a less than 2% overshoot and a 0% steady state error. In order to achieve the 0% steady state error, I will have to use a PI controller. Next, I've uploaded a snip of my code so you can see the constants that went into the transfer function from J down to L. Then you can also see the transfer function, which I had two previous slides ago, which are in the P motor. And finally, the two functions I used to graph this response, which was the step and the systo tool. First graph which I've added here is the open loop response. And you can see as the final value I'm shooting for a 1, and it is not a 1. So in order to reach this requirement, I'm going to have to add the integrator value. On this next slide, you can see I've opened up the root locus and have moved my points to the boundary conditions where my 2% overshoot is located. On the right, you can see the new response of the system. It is important to note from this slide the damping ratio, zeta, down at the bottom right, and the natural frequency, just to the right of zeta. These two multiplied together, and the negative of it equals where my 0 was located, and this is just shy of negative 0.6. If I have this 0 value, I can then go to my compensator and add the 0 plus the integrator. Also, I want to note that I changed my gain from right at 17 to 30 in order to speed the system up. That way the final value wouldn't take so long to reach. This is the system once the controller has been added. As you can see, the overshoot is just over 1%, which is what I was looking for, and the final value is exactly 1, so I have reached both of my design requirements. As a final step, I exported my compensator equation out to the MATLAB home screen, that way I could see it, and here you can see it. Which brings me to the end of my presentation. Thanks for watching, and if you have any questions, please shoot me an email.